Alright, so let me just write down what I said last time. So we are trying to prove Marty's theorem, which is it's an analog of Montel's theorem for meromorphic functions. Okay, and we've just so what I've written here is up to one way of the proof of the theorem, okay, namely that if you have normal uniform boundedness of the spherical derivatives then of a family of meromorphic functions defined on a domain in the complex plane, then that family is compact in the sense that it's normally sequentially compact, namely that given any sequence in that family you can find a subsequence which converges uniformly on compact subsets of your domain. Okay, so and I just told in words the proof that the other way of the theorem is also true, that namely, suppose you start with a family which is normal, so in the sense that a family which has this property that every sequence admits a normally uniformly convergent subsequence. Okay, then of course this is a family of meromorphic functions. Then the claim is that if you look at the family of spherical derivatives, that family has to be normally uniformly bounded, namely it should be uniformly bounded on every compact subset. Okay, and that's the way we have to write down the proof. I told you in words how this can be done, but now I'll write it down. I'll write it down more accurately. So let me write this here. Conversely, so probably I'll because I'm going to the converse, I'll probably change color, take something else. So conversely, assume that script f is a family of meromorphic functions on D such that every sequence in script f admits a normally uniformly convergent subsequence. So I'm abbreviating uniformly to UFLY. CGT is the abbreviation of convergent, and SUB SEQ is for subsequence. So basically this is the right notion of saying that the family is compact. Okay, what do I have to show? We need to show that the family of spherical derivatives, namely this is the set of all you take each function small f in the family script f and take its spherical derivative, okay, and then you get the family of spherical derivatives of this collection and what you have to show is that this family of spherical derivatives is normally uniformly bounded, okay, is normally. That means that you'll have to show that it is that it is uniformly bounded on every compact subset of T. Okay, what does that condition mean? That is, for every compact subset K in D. So I am using CPT to abbreviate the word compact. So for every compact subset K in D, okay. So let me write it as a logical statement because I am going to negate it, because we are going to prove it by contradiction. For every K in D with K compact, there exists M greater than 0. There is a uniform bound for all the spherical derivatives of the functions in your family when restricted to K. That is, so if I write it down, it means that there exists a uniform bound which I am calling as M, such that the spherical derivative of at each point is bounded above by M for all functions f, small f in the family script f, and for every point z in the compact set. Okay, this is exactly the condition that the family of spherical derivatives is normally uniformly bounded. Mind you, the spherical derivative is a non-negative real number. Okay, the spherical derivative is a non-negative real number. It's 2 times the modulus of the usual derivative divided by 1 plus modulus of the function squared. Okay, and this is at all the points where the function is analytic, and since we are considering meromorphic functions, you could have points which are poles, and at poles I have told you what the spherical derivative is. We have evaluated it by continuity. If the pole is a simple pole, the spherical derivative is 2 divided by the modulus of the residue of the function at that simple pole. Otherwise it is 0 if it is a pole of higher order. Okay, and of course for this exceptional function which is constantly infinity on the whole domain, which is also possible in a limit of meromorphic functions, or even for that matter even for analytic functions under a normal limit, for this function which is constantly infinity equal to infinity, the spherical derivative is 0. Okay, we should remember that. So so here is so what we have to show is that we have to show this condition. Okay, and what we will do is we will prove by contradiction. So what we will do is we will assume this condition is not going to hold, and we will contradict the fact that you have normality of the family, namely that every sequence in the family admits a subsequence which converges uniformly on compact sets. So we will do that. We will show a counter example to that. Okay, so so suppose the above does not hold. So this is proof by contradiction. Suppose this does not hold, then what do you do? So you know what you will have to do is I will have to negate this. Okay, I have to negate this logical statement. Okay, and you know there is a very slick way of negating logical statements. You normally replace for every with there exists, and the other way around, you replace there exists with for every. Okay, that's the way you do it. So you know, if I negate this, what I will get, for every compact subset I want a certain property to hold. If I negate it, it means that there I can find a certain compact subset where this property will not hold. So this for every k in D with k compact will negate to there exists k in D with k compact. So it will become there exists k subset of D with k compact. Okay, and what is the rest of it? So look at the original statement. For every k in D with k compact, there is this is the rest of the statement. The statement is that for every f and for every z, okay, I can find an m such that the spherical derivatives of f at z are all bounded by m. Okay, so this there exists m greater than 0 upon negation will become for every m greater than 0. Okay, and this for every small f will become a there exists small f, and this for every small z will become there exists a small z. So the way this part negates is you will get for every capital M greater than 0 there exists an f sub m in the family, okay, and a point z sub m in the compact set such that the spherical derivative of f sub m at z sub m is going to be greater than m. This is how it negates, okay. This is the negation of that statement. So in particular what I can do is that, you know, basically I want to show that if I assume that this happens, I want to show that I am going to get a contradiction, and contradiction to what? Contradiction to what I have assumed, namely that the family, whenever you have a sequence you can extract a normally convergent subsequence, okay. So so I will have to cook up a sequence, and the way I do it is, since this negated statement is true for k, you start putting m equal to 1, 2, 3, 4, so you make m larger and larger so that m goes to infinity, and then, you know, by going to infinity you expect that the spherical, what you will get is you will get a sequence of points and a sequence of functions where the spherical derivatives at those corresponding points is going to infinity, but then this cannot be this cannot come from the original family if it were normal. That is because normal convergence of a family also implies normal convergence of the spherical derivatives, and mind you, the spherical derivative is a finite quantity, okay. It cannot go, it's not an infinite quantity, okay. So that's how we will get the contradiction. So what I will do is, so let me write it down. These are gory details, but sometimes you should know how to write down things, that's very important, and sometimes you should also be able to just say it in words. For example, you would find in several textbooks probably the textbook would become very voluminous if they write down every detail, so they might just qualitatively say it in a few words, okay, but then it's your duty to write it down, you have to translate it, okay. So this is part of this exercise whenever you read a book, okay. But since this is a lecture, I am bound to explain as many details as I can, so I will do it. So put m equal to 1, 2 and so on, get f1, f2 and so on. These are all functions in the family script f, and you get these points z1, z2 and so on, which these are all points in k with the spherical derivative of fi at zi greater than I, okay. I get this. This is when I put m equal to 1, 2 and so on, okay. Now you know how the proof will go. On the one hand, I have this sequence of functions, so I can always extract a normally convergent subsequence because that's part of my assumption, okay. On the other hand, I also have this sequence of points, okay. It's a sequence of points, but where does it lie? It lies in a compact set. Therefore there is a convergent subsequence, because, you know, this compact set is a compact metric space, and for a compact metric space, you know, that means compactness is equivalent to sequential compactness, which means that from every sequence you can extract a convergent subsequence. So what I can do is that I can do it either way. So let me do it like this. Since k is compact, so sequentially compact, because compactness and sequential compactness are equivalent for metric spaces, there exists subsequence z. Let me call this as Zn Zn I, okay. There is the subsequence which converges, okay. It will converge to a point, and that point has to be in k, because, you know, a compact set is closed, okay. Because a set is closed, so if a set is closed, it will contain limits, okay. So Z sub ni is a subsequence, and it's a convergent subsequence, so the limit should also be in k because k is closed, okay. Fine. So you have this. So you have these Zni's going to Z0 on the one hand, okay. This is the compactness of k where that's being used, and then I'll also use the fact that the family is normal, okay, that it is compact, okay. So by hypothesis, there exists a subsequence so, you know, well, there exists a subsequence of f sub ni, okay. So you see I already have the original sequence, okay, and I have the original sequence of points. When I take a subsequence of points which converges, I have gotten a subsequence of the original sequence, and I am considering the corresponding functions in the family of in the sequence of functions, and I am that's already a subsequence, and I am extracting a further subsequence from that, because that's what the normal sequential compactness is all about. From give me any sequence, I can always extract a normally convergent subsequence. So I'm not extracting a convergent a normally convergent subsequence from f1 f2 and so on, but I am extracting a normally convergent subsequence from the subsequence given by fn1 fn2 and so on, okay. So so there is a subsequence of fni, say let me call this as, well, the notation gets a little bit bad, but it does not matter. So I get this subsequence, I get a subsequence of this which converges uniformly on K, okay. In fact, it will be a subsequence which will converge uniformly on all compact subsets of D, okay. That is what the theorem, that is what the hypothesis promises, but I am restricting, I am just worried about K for the moment, because K is a compact set when I am working. Now, but here is the issue. The issue is that these this FNIL, okay, this will go to certain F0, okay, because you see a normal limit of if you take a normal limit of meromorphic functions, that is also meromorphic, that is something that we proved, okay. See, a normal limit of meromorphic functions is either identically infinity, okay, or it is a meromorphic function. It can even be holomorphic, okay. This is what we have already seen, okay. So this f0, what can happen with f0 is that f0 can either be the function which is identically infinity, or f0 can be a honest meromorphic function, it could even be a holomorphic function, okay. So note that either f0 is identically infinity, okay, or well f0 is meromorphic function on T, okay. So this is there, alright, and what is it that I want you to understand? See, this convergence is uniform on K. This FNIL converges to f0 is uniform on K. It is a uniform convergence. So what it means is, given epsilon greater than 0, okay, that you can find an n such that if your I sub l is greater than n, all right, then the distance between these two functions, the distance between the function values at any point of K it can be made less than epsilon. And mind you, now because you are working with meromorphic functions, they could very well take the value infinity, and you should not use the usual distance, you should use the spherical distance. So you'll have, so I have tried it like this: d spherical of f of nil, f sub nil of z, comma f0 of z, this can be made less than epsilon, okay. The spherical distance between the value of these two, the functions in the sequence beyond a certain stage and the value at the limit, that can be made as small as I want. This is uniform convergence. So, and the point is that this n has got nothing to do with z. So this is for all z in K. This is the uniformity. It works for all z. Okay. So so in particular, you can now see what I am getting at. You see, I have these znis. These znis are going to z0, okay, and therefore the f, if you give me any function f in the family by continuity, f of zni will go to f of z0, alright, and but the point is, for f, if I had taken fni, okay, what will happen if you take the original sequence of functions f1 f2, and so if you take fi and evaluate it at zi, not the function but I mean the spherical derivative, okay, then it is greater than I, okay, we have this. So if I take this fni and evaluate and take its spherical derivative and then evaluate at zni, I am going to get something that is greater than ni, okay. and that is supposed to go to Fni of z0, and now if I let ni tend to infinity, it will go to f0 of z0. So essentially, f0 of z0 is going is coming very close to a sequence of quantities which are becoming larger and larger. Then how can it be? Because I mean not f0 of z0, but I mean spherical derivative of f0 of z0. So let me write it out. Yeah. So the first statement I need to make is so this was the lemma that I had rubbed out last time. So this lemma is that if Gn converges to G normally in suppose this is a normal convergence, then the spherical derivatives also respect that. So then the spherical derivatives of the Gn's will go to the spherical derivatives of G normally. Okay. So this is the lemma that I rubbed out, which we need to use at this point. If you have a sequence of meromorphic function which converges to a limit function, and suppose all this is happening normally, namely it's happening uniformly on compact subsets of your domain D, then of course we have already seen that the limit function is going to be meromorphic, or it is identically infinity. Okay, so this G can be either meromorphic or it's identically infinity, and the point is no matter what that is, if you take the corresponding sequence of spherical derivatives, that will converge also to the spherical derivative of the limit, and that will happen normally. Okay, and remember that if G is the function which is identically infinity, there is no problem with the spherical derivative, it is 0. It's not something that's strange. Okay, it's not an undefined quantity or something like that. Okay, so you have this. So I'm using this. So if I use this, what will I get? What I'll get is that, you see, I have this Fnil going to f0. So this will tell me that Fnil, the spherical derivatives will go to f0, spherical derivative of f0. Okay, and this is happening. Mind you, this is going to happen normally. So it's going to be all this is going to happen uniformly on K. Okay, so this is uniformly on K because K is compact. All right, and what does this mean? This means that if you calculate, mind you, when I am comparing values of usual meromorphic functions, I will have to use the spherical metric. Okay, but when I am comparing values of the spherical derivative, okay, I have to use the usual distance function on R because spherical derivatives are non-negative real numbers. So what this means is that given an epsilon prime greater than 0, there exists an n prime such that if the index is greater than n prime, then the distance between Fnil hash and f0 hash or for at any z can be made less than epsilon prime. Okay, I can do this for all z in K. This is what it means, and I am using the modulus function here because these values are all real values. Okay, you see, I will now interpolate. So what I will do is that I will use a triangle inequality and write this as Fnij of Zij, and then I will add f0 of Zij. Okay, I can do this, plus then I will write this f0 of Zij minus f0, and of course everything is a spherical derivatives, not just the original functions. So and then I will have f hash of z0. So this is just by the good old triangle inequality on the real line, right? I have just added and subtract the spherical derivative at Zij, okay, and of f0. Okay, so now you know what I am going to do. So this will be Nij. That's what this quantity is. All right, and now you know, by now you know what's happening. You see, this quantity is Nij, and as Ij tends to infinity, this is going to go to infinity. Okay, this is going to go to infinity as Ij tends to infinity. Okay, you know that. All right. So what you are saying is, what is there on the left is the distance from f0 hash of z0, okay, to to a value which is going bigger and bigger, and you're saying that can be bounded by the sum of two quantities. Okay, see the first quantity, see the first quantity can be made less than epsilon. That's because of the uniform convergence of Fnij to F naught. Okay, see I've just written it down above. The Fnij's, they converge uniformly to F naught on K. So the lemma says that therefore the spherical derivatives also converge. So the distance between Fnij hash and F naught hash at any point can be made as small as I want. So the moral of the story is that this quantity here can be made less than epsilon. Okay, and this is okay. This is okay for any z. Okay, so I plug in Zij, so I can make this less than epsilon. Okay, and look at this quantity here. What is it? So this is less than epsilon. Of course, I'll have to put in some condition, and the condition is that if this Nij is chosen greater than n, I think it was so it is less than epsilon prime if you choose the ij greater than n prime. So let me write that. So it is, this can be made less than epsilon prime if, so let me write it correctly, ij can be made greater than n prime. Okay, I can do this, right? And again I think I missed the subscript needs to be corrected here, so let me do it. Oops, yeah, this is an issue with double subscripts or triple subscripts. Okay, so this quantity, this can be made less than epsilon. Okay, so I have this, and then what about the second quantity? The second quantity is the spherical derivative at so there's a zero missing here. The spherical derivative of f naught at Zij minus the spherical derivative of f naught at Z naught. Okay, but mind you, this also I can make sufficiently small. That's because of the continuity of the spherical derivative. The spherical derivative is anyway continuous. Okay, so the moral of the story is that I can make this also. This also can be made less than, if you want, epsilon double prime, if you choose some. Yeah, again I have this this problem cropping up that I'll have to worry about this double subscript. Let me write this Nij. If n sub ij, if ij is sufficiently large, is greater than say n double prime, I can do this. And this is just what am I using here? I'm just using, I don't have space to write, but maybe I'll continue here. Continuity, use continuity of f naught hash at Z naught, and remember that the Z Nij's also tend to Z naught. The Z naught was a limit point. Okay, so that's it. You have a quantity on the left, okay, which is very close to a very large number. Okay, and this large number is becoming larger. That it is very close to a large number is because it's bounded by a quantity on the right which is very small. Okay, the sum of epsilon and epsilon prime, I can make it as small as I want. So it means that the quantity on the left, which is the spherical derivative at Z naught of f naught, that comes arbitrarily close to any large number. Okay, and that's impossible because this is a contradiction, because this quantity is a finite quantity. The spherical derivative at any point is a finite quantity, so it cannot be within an epsilon distance of an increasing sequence of numbers. It just can't happen. So that's a contradiction. So let me put this here. So this is a finite quantity, and the totality of all is that that the whole thing that you've written down managed to get is absurd. Okay, so let me write that down. So this is absurd. Okay, all this is absurd. Can't happen. So we get a contradiction. Okay, and that finishes the proof. Okay, so spherical derivatives need to be bounded. Okay, And the point I want you to remember is that, of course, sometimes writing down these gory details is a pain. You'll have to worry about subscripts and things like that. But then once in a while you should do this, because then you get a feel of having written down something very accurately. Okay, and of course you also should try to be very elegant and say without any notations. You must be able to just say in words. So if you want to say all this crazy thing in words, what you would say is that, well, I have a sequence of points and I have sequence of functions which if I want to prove by contradiction, I will find a compact set on which the uniform boundedness of the derivatives will not be true. On that compact subset I can get a sequence of functions and a sequence of points such that the corresponding spherical derivatives are going to be unbounded, okay, and but then the points have to converge because it's a compact subset. At least a subsequence of points have to converge because it's a compact subset. Okay, so and also the functions must allow a convergent subsequence. If you put these two together, what will happen is that you will get a sequence of spherical derivatives becoming unbounded, okay, but coming arbitrarily close to the spherical derivative of the limit function at that given point, and that's not possible because the spherical derivative of a function at a given point is a finite quantity. Okay, so that's how you can say it elegantly in words. Okay, fine. So that finishes Marty's theorem. So mind you, Marty's theorem is very, very powerful, because you see it's more powerful than the usual Montel theorem, because you see Montel's theorem, the original Montel's theorem says that it's only for analytic functions, and what you had required there was you needed normal uniform boundedness of the family of analytic functions. All right. Whereas in Marty's theorem you generalize from analytic functions to meromorphic functions, okay, and you don't require normal uniform boundedness of the functions, but you require normal uniform boundedness of the spherical derivatives of the functions. Okay, so this is the difference. So suppose I have a family of analytic functions, okay, and suppose I know that their derivatives are uniformly bounded, normally uniformly bounded, okay, I can still conclude something from I cannot apply the original Montel theorem, okay, but I can apply Marty's theorem and say that I can still conclude that this family of analytic functions will converge to a limit, and since it is normal convergence, okay, if you take a sequence of functions from this family, I can extract a subsequence that will converge to a limit, and that limit will either be holomorphic or it will be identically infinity. So you see, Marty's theorem is more powerful. That's what I want to tell you. Okay, so let me again go back to that slide that I wrote out. Here it is. So let me go back to this slide. You see, there was this thing that I have circled in violet, surrounded by a small. I have written it in red. The family of derivatives is normally uniformly bounded as an intermediate step. Okay, so if I start with the family which is normally uniformly bounded, and suppose it's a family of analytic functions because of the Cauchy integral formula, okay, I get that the family of derivatives is normally uniformly bounded, okay, and from there I get equicontinuity, and once I have equicontinuity and uniform boundedness, I can apply the Arzelà-Ascoli theorem, okay, and then whatever I want I get by doing a diagonalization argument. But now you see, suppose I am given a family of analytic functions, okay, on a domain. Suppose I am not given that the family is normally uniformly bounded. Suppose I am not given that, okay, I cannot apply the original Montel theorem. Suppose I am given instead of being given that the original family of analytic functions is bounded, suppose I am given that the family of derivatives, usual derivatives, which makes sense for analytic functions, suppose I am given that family is normally uniformly bounded, okay, I cannot apply Montel's theorem because I don't have the uniform boundedness, normal uniform boundedness of that family itself. I have only the normal uniform boundedness of the derivatives of the family. I cannot apply the usual Montel theorem. But then the uniform boundedness of the boundedness of the ordinary derivative will imply the boundedness of the spherical derivative, because of this inequality. You see, if you go down, because that's the so this is what I have circled in violet. You see the spherical derivative is bounded by 2 times the bound for the normal derivative, the usual derivative. So if I am given a family of analytic functions such that the usual derivatives are normally uniformly bounded, it follows that the family of spherical derivatives is normally uniformly bounded. Okay, so I can apply Marty's theorem. Marty's theorem will tell me now therefore that any sequence in that family admits a convergent subsequence, a normally convergent subsequence. Okay, and that normally convergent subsequence is what? It's a convergent sequence of holomorphic functions, but the only thing is that the convergence is with respect to the spherical metric. And then you know what happens? My limit function will either be holomorphic, that is analytic, or it will be identically infinity. Okay, so what is the upshot of all this? The upshot of all this is, let me state it. If you have a family of analytic functions on a domain, and suppose you know that the usual derivatives of the analytic functions are normally uniformly bounded, okay, then that family is compact in the sense that give me any sequence in that family, I can find a subsequence of convergence, normally convergent subsequence, and the limit function will either be again analytic or it will be identically infinity. This is what I will get because of Marty's theorem. And mind you, I cannot apply the original model theorem, because for the original model theorem I need boundedness, uniform boundedness on compact subsets of the original family. That is not given to me. What is given to me is only uniform boundedness on compact subsets of the derivatives. Okay, so in that sense, Marty's theorem is very, very strong. It's stronger than Montel's theorem. Okay, so with that, you know, I have more or less we have more or less come to one point here in our discussion. I will tell you what we need to do next. Okay, so if you see in all these things that we have proved, we have been looking at a domain in the complex plane. Okay, so what are the things that we proved? First, we proved that for a domain in the complex plane, we defined normal convergence. Okay, that is uniform convergence on compact subsets. And then we proved that if you take a normal limit of analytic functions, okay, then the limit is either identically infinity, okay, if you use a spherical metric, or it will be again an analytic function. Okay, and if you take same thing happens for meromorphic functions. If you take a family of meromorphic functions, okay, if the family, for example, if you take a sequence of meromorphic functions which is normally uniformly convergent, then the limit function is again going to be either meromorphic or it will be identically infinity. You don't get any strange situations. Okay, the moral of the story is when you take a normal limit of analytic functions, you will get an analytic function, and the extreme cases you will get the function is identically infinity. Same for meromorphic functions. Okay, and we have seen that, for example, if you take a sequence of meromorphic functions, is not going to go to a sequence of analytic functions is not going to go to a strictly meromorphic function. Okay, a pole cannot pop up at you at the limit. Okay, such things cannot happen. So it's all very well behaved. And then we have proved the Montel's theorem and we have proved Marty's theorem. Okay, now all this is for usual domains. What about a domain which contains the point at infinity? That's the next. We want to extend all these results to a domain in the extended plane. What is the problem with the domain in the extended plane? The problem with the domain in the extended plane is the point at infinity. For the point at infinity, okay, you cannot find a compact neighborhood, at least on the usual plane. Okay, so if you take, suppose D, so what I am trying to say is that, you know, if you say that if I am taking a domain in the extended plane, that means it's actually a domain in the usual plane. It's in the exterior of a large enough disk, and it includes the point at infinity. Okay, and whenever I take compact subset of that, it will not include the point at infinity. The point at infinity cannot come into any compact subset. Okay, so there is a problem. If you take a domain which contains a point at infinity, okay, you are never able to get a compact neighborhood of infinity in the usual sense. Okay, so what is the meaning of normal convergence at infinity? That has to be made sense of. You have to understand what normal convergence at infinity means. You will have to understand that in that context you have to extend all these theorems. Okay, so what I will do in the coming lectures is try to look at normal convergence at infinity and extend all these results to the case when your domain is a domain in the extended plane which can possibly contain even the point at infinity. Okay, so this is a very, very important step. Okay, and then we have enough tools to go ahead with with another theorem called Zalcman's lemma, and that will lead directly to a stronger version of Montel's theorem on omission of values, and that will lead to finally to the Picard theorems. Okay, so we will see that in the forthcoming lecture.